Bismillahirrahmanirrahim. We were discussing about the fuel cell. We have learned about the operation of the fuel cell, how fuel cell works. We have learned about the comparison of fuel cell with heat engine and batteries. We have learned about the Faraday constant. We have learned about the stoichiometry, Faraday efficiency, and we have done some problem related to the fuel cell. Now, in this lecture, we will determine the maximum thermodynamic efficiency of a fuel cell. So, first to understand the maximum thermodynamic efficiency of the fuel cell, we will discuss about Gibbs function. Gibbs function is an thermodynamic property and it is defined from other thermodynamic properties like enthalpy and entropy. We use enthalpy and entropy in order to define the Gibbs function. It is a combination of different thermodynamic property. That's why it is also a thermodynamic property, and it is given by H minus Ts, where capital H is the enthalpy, T is the temperature, and S is the entropy. Gibbs function is a measure of maximum work possible at a given state from a constant temperature and pressure reversible process. If we have a reversible process at constant temperature and pressure, then the amount of maximum work possible from that process is given by the Gibbs function. It is nothing but the maximum possible work from a reversible process at constant temperature and pressure. It can be shown from a combination of first and second law of thermodynamics for a simple compressible system that the Gibbs function of a system will always decrease or remains the same for the spontaneous process. If we use first and second law of thermodynamics, then for a simple compressible system we will see that Gibbs function will always decrease or remain same for a spontaneous process. But one thing which we should learn about from this Gibbs function concept, that this is the thermodynamic property and it is the measure of maximum work possible from the process which is occurring at constant temperature and pressure, and that process should be reversible. Gibbs function is entirely applicable to a reversible process. I think that Gibbs function is new concept for you, and it is nothing but a simple thermodynamic property. Now we are discussing about the thermodynamic efficiency of a fuel cell. Fuel cell is simply a energy conversion device, so it should satisfy the laws of thermodynamics. That We know that first law of thermodynamics is nothing but the conservation of energy. That energy can neither be created nor be described, but can be transformed from one form to another form. Since the fuel cell is the energy conversion device, so it should follow the first law of thermodynamics. And in fuel cell, the initial chemical bond and energy available as the difference between the enthalpy of the product and reactant in a galvanic process is conserved, but it is converted into electrical energy, current and voltage, and thermal energy. In fuel cell, chemical energy is converted into electrical energy and heat. When hydrogen and oxygen electrochemically combined, we know that in hydrogen we have hydrogen and oxygen both are chemical, so they have chemical energy, bond energy available. So that bond energy, which is the chemical energy, that chemical energy in a fuel cell is converted into electrical energy and thermal energy, but the overall energy will remain conserved. But we use fuel cell in order to convert the chemical energy into electrical energy. We know the purpose of a fuel cell is to convert chemical energy into electrical energy, not into heat. We use fuel cell to convert chemical energy into electrical energy. We do not use fuel cell to convert chemical energy into heat. So the desired output of the fuel cell is the electrical energy. And the thermodynamic efficiency of the fuel cell can be written as actual electrical work divided by the maximum available work. We know the actual electrical work is the required output of the fuel cell, because the main purpose of the fuel cell is to convert the chemical energy into the electrical energy. So that's why its desired output is actual electrical work and input is maximum available work, which is in the form of chemical energy. Now, what will be the maximum electrical work for a reversible system? We are discussing about the maximum electrical work for a reversible system. We are going to consider a generic reversible system with mechanical and electrical work and heat transfer at constant temperature. From first law of thermodynamics for simple compressible system, if we have simple compressible system, then first law of thermodynamics will be written as du is equals to delta q minus delta w. This is the first law of thermodynamics, that internal energy of a system is the difference of heat and work output. Here delta q is the heat interaction and delta w is the work from the system, and du is the change in internal energy. I hope that you know why we do not use D with Q and W. Instead of using D with delta Q and delta W, we use delta with heat and work, because heat and work are path functions. They are not thermodynamic properties, where U is the internal energy and it is the thermodynamics property, and with thermodynamic property we can use differential, but with path function we use delta. So this is the simple first law of thermodynamics. Du is equals to delta Q minus delta W. Now in fuel cell we are considering that delta W means the work can be divided into mechanical work, which is the expansion work, and electrical work. In fuel cell both work are possible, the mechanical expansion work and the electrical work. So we can write delta W is equals to PdV plus delta WE. PdV is nothing but the mechanical work and delta WE is the electrical work. So work is divided into mechanical as well as electrical work. Now for a reversible system, the second law of thermodynamics can be written as, we know that second law of thermodynamics is related to entropy generation, and for a second law of thermodynamics, from second law of thermodynamics, delta Q is equals to TdS, as more heat interaction, more entropy will be generated, or more entropy generation will responsible in more heat generation. So from second law of thermodynamics, delta Q is equals to TdS. Now we are going to use differential change in Gibbs free energy for a constant temperature reaction. We have learned Gibbs free energy as G is equals to H minus Ts, and differential Gibbs free energy will be dG is equals to Th minus S dt minus Tds. This will be the differential change in Gibbs free energy. But we are talking about constant temperature process. So for constant temperature process, dt will be 0, and we can write dg is equals to dH minus Tds. This will be the differential change in Gibbs free energy for a constant temperature reaction. Now we are going to discuss the differential change in enthalpy. We know that enthalpy is given by H plus enthalpy is the combination of internal energy plus PV. Enthalpy is U plus PV. So for differential change in enthalpy, it will be dH is equals to du plus P dV plus P dP. This will be the differential change in enthalpy. Now term this equation as equation 5. Now we are going to substitute equation 2 and equation 3 in equation 1. This was the equation 1 and we are going to substitute equation 2. If we go back to equation 2, what was equation 2? Now closely look, this was the equation 2. The delta W is equals to P dV plus delta W E. This is the equation 2 and we are going to substitute this equation 2. This was the equation 3. We are going to put the value of delta W and delta Q in first law of thermodynamics. Du is equals to delta Q minus delta W. Delta Q will be replaced by TdS and delta W is replaced by PdV plus delta WE. Because we have mentioned that work can be divided into maximum electrical work and the mechanical expansion work. That's why we can write du is equals to TdS minus PdV minus delta WE. Now term this equation as equation number 6. Now substitute this equation 6 in equation 5. We are going to replace du in equation 5 by the value of du in equation 6. In equation 6, du is equal to TdS minus PdV minus delta WE, and we are going to replace du in equation 5, which is the differential change in enthalpy, by du. If we substitute du from equation 6 in equation 5, then we have equation like this, that dH is equals to TdS minus PdV minus delta WE plus PdV plus PdP. Minus PdV plus PdV will be cancelled out and we will left with an equation dH is equals to TdS minus delta WE plus VdP. This will be the change in enthalpy for constant temperature process. But in fuel cell operation, pressure also remains constant. There will be no change occur in pressure in fuel cell. So we can write dP is equal to 0 because for constant pressure process it means that pressure is not changing. So dP is equal to 0 and dH is equals to TdS minus delta WE. This will be the change in enthalpy for constant temperature and pressure process in which we are extracting electrical work. Now we are going to rearrange this equation. We can also write delta WE, which is the electrical work, is equal to minus dH plus TdS. Now remember the differential change in Gibbs function for a constant temperature process. From equation 4, this was the differential change in Gibbs function for a constant temperature process. The differential change in Gibbs function is dH minus TdS. So we can replace dH plus TdS by dG. So maximum electrical work will be negative of dG. Now what does it mean? This means that maximum electrical work is responsible for change in Gibbs free energy, and electrical work will be taken as long as the Gibbs free energy is available or change in Gibbs free energy is possible. Since this derivation was done for a reversible system, it is an expression of maximum electrical work possible from a system. We have assumed a system to be reversible, and for a reversible system the maximum electrical work possible from a system is equal to negative change in Gibbs free energy. Therefore, the change in Gibbs free energy is related to the maximum conversion of chemical to electrical energy for a given reaction. That's why we can say that maximum conversion of chemical energy into electrical energy is basically the change in Gibbs free energy. I hope that this derivation is clear up to you, that how we can determine the maximum electrical work from a system, and the maximum electrical work from a reversible system is basically equal to the negative change in differential Gibbs free energy. It means that the electrical work is responsible due to change in Gibbs free energy, and for a reversible system Gibbs free energy always decreases. That's why you are seeing negative sign. This will be the maximum available maximum output from the work, or extracted electrical output from a fuel cell. Now we are going to discuss the maximum expected voltage, because fuel cell is a device which converts chemical energy into electrical energy, and electrical energy is nothing but pressure but current and volume. Electrical energy is simply current and voltage. If we have current and voltage, then we can say that we have electrical energy or electrical power. Electrical work is simply given by W is equals to NFE. It is nothing but, I hope that simply you learn electrical work in terms of QV. If we define voltage as work done per unit charge, then electrical work will be the product of voltage and charge. We know that electrical work is the product of voltage and charge, and electrical work will be given by NFE. Here N is the number of electrons involved in 1 molar reaction, F is the Faraday constant, and E is the voltage. Here E is not energy, it is voltage, and we have used symbol E because we commonly use E to designate a voltage based on the concept of electromotive force. That's why we have used symbol E, because symbol E is normally used for electromotive force. So this will be the electrical work. Electrical work is nothing but product of charge and voltage, or we can say that electrical voltage or electromotive force will be WE over NF. We have rearranged the above equation in terms of E. Now, maximum possible reversible voltage. We are going to consider the maximum possible reversible voltage of an electrochemical cell, which is represented by E naught. The maximum possible reversible voltage from an electrochemical cell is represented by EW, and it will be given by minus delta G over NF, because electrical work is due to change in Gibbs free energy. That's why we have replaced WE by minus delta G, which will be the maximum possible reversible work. And due to maximum possible reversible work, we have maximum possible reversible voltage represented by E naught, and it will be nothing but minus delta G over NF. This will be the maximum possible reversible voltage. Maximum possible voltage that can be extracted from a fuel cell, where E naught is called the reversible voltage because it is the maximum possible voltage without any irreversible polarization losses. This is the maximum possible voltage from a fuel cell without any irreversibilities in a system. While in a real system we have a lot of irreversibilities, so we are not considering those irreversibilities. We are considering thermodynamically ideal system. So for thermodynamically ideal system, which is the reversible system, E naught is the maximum possible voltage without any irreversibility. Now we are going to consider thermal voltage. In fuel cell, normally chemical energy is converted into the electrical energy and heat. What if entire chemical energy is converted into electrical energy? It means that there is no losses due to heat. Normally there are losses due to heat in fuel cell because from fuel cell we get electrical energy and heat. What if we get no heat from a fuel cell? It means that chemical energy is entirely converted into the electrical energy. So if it occurs that chemical energy is completely converted into electrical energy, there will be no heat generation, then there will be no heat transfer, and if there is no heat transfer, there will be no entropy generation. So for no entropy generation, the differential Gibbs function will be equal to dH for constant temperature for constant temperature process. Differential Gibbs function is dH minus TdS. If there is no entropy generation, means there is no heat transfer, or we are going to considering isentropic process. We know that what is isentropic process? Isentropic process is a combination of reversible and adiabatic process. We have reversible process, and if there is no entropy generation, it means we have isentropic process, then the Gibbs free energy will be equal to dH. This will be the maximum conversion of enthalpy into Gibbs free energy. Or in this case, we can say that E double dot is equal to E thermal, which is the thermal voltage, equal to minus delta H over NF. It means that entire chemical energy is converted into electrical energy. There is no conversion of chemical energy into heat. There is no heat generation. It means that there is no entropy generation. Due to no entropy generation, change in Gibbs free energy is equal to change in enthalpy, and the maximum voltage from the system will be equal to minus delta H over NF. We have replaced delta G by delta H. Here E naught naught is known as the thermal voltage for a reaction and is the maximum voltage for a reversible adiabatic system. It is the maximum voltage for an isentropic process or for a reversible and adiabatic system. So this will be the maximum available voltage, and E naught is the maximum output voltage. Since there is an entropy change associated with every real reaction process, this voltage is merely a limit representing the case of all chemical energy converted into the electrochemical work with no heat transfer or change in available microstates entropy. Normally, we have entropy generation, we have no isentropic process, we have reversible process, and we have entropy generation. So E double dot is entirely a limiting case in which all available chemical energy is converted into the electrical energy. So this is basically the available energy. we can say that this is the available voltage. Now the ratio of maximum expected voltage, which was the E naught, to the thermal voltage, which is the maximum available voltage. E naught is the maximum expected voltage and thermal voltage is the maximum available voltage, represents the maximum electrical work to the total available potential electrical work. The thermodynamic efficiency possible will be, this is the thermodynamic efficiency, that maximum electrical work over maximum available work. Maximum electrical work is basically represented by minus delta G over NF, and maximum available work is represented by minus delta H over NF. This is the maximum electrical work and maximum available work. Maximum available work means that entirely chemical energy is converted into electrical energy. This will be the maximum available work. While maximum electrical work consider entropy generation within the system. Maximum electrical work consider maximum electrical work consider totally reversible system with entropy generation. But maximum available work means entire chemical energy is converted into the electrical energy. Or we can write thermodynamic efficiency is the ratio of E naught over E double dot, means the ratio of maximum expected voltage to the thermal voltage. By simplification, we can write delta H minus T delta S over delta H. We have replaced delta G by delta H minus T delta S, considering constant temperature process. So this will be the thermodynamic efficiency of a fuel cell, or we can write the expression of the maximum possible thermodynamic efficiency of a fuel cell as 1 minus T delta S over delta H. This will be the maximum thermodynamic efficiency of a fuel cell. Now carefully look that thermodynamic efficiency of a fuel cell is not limited by Carnot efficiency, which is for heat engine. Due to this expression, fuel cells are considered to be more efficient than heat engine thermodynamically, and this will be the expression for maximum possible thermodynamic efficiency for a fuel cell. Now look at the graph. This graph is basically a comparison of maximum thermodynamic efficiency for heat engine and fuel cell engine. We have compared thermodynamic efficiency of heat engine and fuel cell engine. We have considered an ideal case. Means for heat engine the ideal case is Carnot cycle, and we have considered a fuel cell in which we have reversible process. Now carefully look at this graph. This graph shows that at low temperature, fuel cell is much more efficient than the heat engine. This graph is simply showing that fuel cells are much more efficient than heat engine at lower temperature, and it is not possible that always fuel cell will have a greater efficiency. At higher temperature, heat engine will consider more efficient. So if you read point number 1, the plot shows that the maximum thermodynamic efficiency is not always greater for a fuel cell. At high temperature, a heat engine can theoretically be more efficient. In terms of thermodynamic efficiency, fuel cell will not always have high efficiency. It might be from this graph it can be evident that at high temperature heat engines are more efficient than fuel cell, but at low temperature fuel cells are considered to be more efficient, and you can see that from this graph. The plot only shows the maximum possible efficiency which will not be obtained in practice for heat engine or fuel cell. For fuel cell, the efficiency decreases with increasing electrical power, so that it only approaches the theoretical value at open circuit condition where no useful work is produced. This graph is basically related to the ideal efficiency, and we know that ideal efficiency will not be achieved due to some other, we have considered totally reversible process, while our real system are irreversible. There are some irreversibilities left during a process. So this comparison is entirely based on the ideal efficiency. We have considered totally reversible process for fuel cell and heat engine. And in practical applications, the electrical power of the fuel cell or the electrical efficiency of the fuel cell decreases with increasing electrical power. So it will only approaches the theoretical value at open circuit condition where no useful electrical work is produced. We know that at open circuit condition there is no current draw, so that's why there is no electrical power available at open circuit condition. At open circuit condition, fuel cell will be considered to be highly efficient, but as we draw current from fuel cell, the efficiency of the fuel cell decreases. So I hope that this lecture related to the thermodynamic efficiency of a fuel cell is clear up to you. If you have any query, any question related to this lecture, then you can comment on Google Classroom. You can also ask in live session. So this is all from my side. Thank you for watching this video.